My name is Sophia Muscat and this is my mechanical changes presentation. The mechanical changes task that I have examined is the overarm throw. The key variable of interest is the release velocity of this throw, and the implemented change is a longer stride with the front foot, just to observe the comparison between a normal and an exaggerated step to see whether it influences the release velocity. For my video capture, we had a video set up using 250 Hz frame rate, which is ideal for faster movements like an overarm throw, as more pictures are taken through the movement per second, which induces greater accuracy through the tracking process. Shutter speed is the length of time the lens is open for with each image taken, so having a faster shutter speed minimizes the blurring of each image. I set a shutter speed of 250 where the lens is open for 0.004 seconds for each image, allowing for greater image visibility to assist with the tracking process. Manual camera focus was also used for these videos, using the mechanics tutorial video cameras. The subject was instructed to execute an overarm throw including a stride forward. We then repeated this throw but increased the stride forward to examine whether the release velocity of the ball was impacted due to the mechanical change. All of these elements were used to ensure the highest quality data collection. To determine the release velocity calculations, we used a calibrated video position, which allows for kinematic data analysis to be extracted using a proportionate scale. The setup of the camera requires an accurate scale distance, camera angle, and positioning for proper analysis. The calibration involved with my testing included markers on specific joints and the ball for tracking data to be produced from, and a calibration stick that allows for the tracker software to convert pixels into meters of distance. When examining an overarm throw, the video was taken perpendicular to the subject, and the data used meters as a measurement to represent real life release velocity of the throw. The ball marker was used considering the key variable is the release velocity. The positioning of the ball from the start to the release of the throw is needed for further calculations. The Y position on the vertical axis was used during the calculations for velocity as it assists with displacement analysis. So now looking at my results, using the basic formula of displacement divided by the time interval of the ball release, the release velocity can be calculated. So this graph shows the comparison between both videos here in figure 1, where the mechanical change was implemented. So this was found by first finding the displacement of the ball from the start of the throw through each frame to the release. We then divided that value by the time of the movement that it was performed in. So the start and end point measured in the velocity calculations are demonstrated through the images on this slide. The top two are for a normal stride with the front foot, and then the bottom two are for the greater stride. As this test aims to find the launch velocity, a point towards the end of the data set highlights a dramatic value increase, indicating the release velocity before the ball accelerates freely through the air. The results of the video with the normal step forward produced a ball release velocity of 15.7 meters per second, whereas the ball with a greater stride forward produced a velocity of 22.5 meters per second. This is fitting for the subject as the estimated release velocity for an untrained female using a tennis ball sits between 50 to 30 meters per second. So here are some relevant biomechanical concepts. So starting with kinematics. Kinematics describes the motion of the body during movement with respect to the changes with time of the position or orientation. So for an overarm throw, kinematics explores all of the bodily movements involved with the throw to improve performance when position, velocity, acceleration, and displacement are analysed. So displacement in kinematics describes the changing of position throughout a movement, such as the placement of the front foot when stepping into an overarm throw. Velocity is then used in kinematics to observe the rate of change of displacement with time. So specifically for an overarm throw, the velocity at the point of release of the ball indicates the thrown distance and speed, as a higher velocity results in a faster throw with greater airtime. Acceleration then examines the rate of change of velocity. So by achieving maximum linear velocity in the hand upon release of the ball, it will travel faster as acceleration will increase. Having a greater step forward creates more time to perform an overarm throw, simultaneously increasing the acceleration through the movement and therefore release. So now moving on to a momentum. Momentum is measured as mass multiplied by velocity and describes the quantity of motion of an item undergoing movement. In an overarm throw, the sequence of movements through the whole body creates momentum, which is generated, transferred, and delivered through the ball. Momentum is first produced by the lower portion of the body in an overarm throw. This includes the stride forward with the front foot, producing a forwards motion, as well as the simultaneous trunk rotation that generates linear momentum. So momentum is then transferred through the lower portions of the body in the kinetic chain. So it starts from the larger segments up into the trunk and then followed through the upper body with the smaller segments and is finally passed onto the ball that is thrown. This occurs as each segment contributes to the pass of momentum as the movements create an overarm throw is accelerated. The more momentum that is generated then transferred to the ball at release, the greater the speed of the ball through the throw, and therefore more distance that is travelled. So the greater the initial step forward, the more momentum that is generated and transferred onto the ball, and the larger the release velocity. Momentum is vital for throwing efficiency, as the transfer of momentum minimizes energy loss and increases the power of a throw, directly contributing to improved performance. Next, we talk about ground reaction force. So ground reaction force describes the reactive force applied by the ground onto the body in contact with respect to Newton's third law of motion that states for every action there is an equal and opposite reaction. So in the case of an overarm throw, ground reaction forces are present from both the push-off on the back foot and the planting of the striding front foot. So just focusing on the forward stride, once the foot plants onto the floor, a ground reaction force is generated both vertically through the body and onto the ball, as well as horizontally where the energy is transferred in a forward motion, initiating energy buildup. Contact with the ground allows for stabilization and ease of the lower segments of the body to create a foundation for a powerful throw execution. When an athlete executes a greater stride forward with the force and energy transfer, a greater ground reaction force is produced, which contributes to an increase of acceleration and therefore ball velocity projection. So ground reaction forces and momentum go hand in hand to the contribution of energy efficiency transfer upwards and through the body and into the projection of the ball, improving the launch velocity and overall performance from the athlete. Lastly, we talk about projectile motion. So projectile motion refers to an object being projected into the air and only being affected by gravity and air resistance. Projectile motion can be both horizontal and vertical. However, gravity only influences the vertical portion of the projectile as it holds constant acceleration vertically towards the earth at 9.81 meters per second. During an overarm throw, the ball being thrown into the air is known as a projectile. So projectile motion is an important biomechanical concept as it allows for an understanding of the travel parameters of the projectile and how these elements contribute to improved sports performance. Calculating projectile motion uses the laws of constant acceleration with respect to displacement, acceleration, and velocity. As we know, velocity is constantly decreasing during upward flight until it reaches its peak where velocity hits zero, then begins to increase during downward flight. These vertical kinematic factors mirror each other because of gravity as the motion remains symmetrical due to the constant applied force onto the projectile. This reveals the importance of initial launch speed and velocity of the ball following an overarm throw, as an inefficient transfer of energy and loss of speed as the ball is released is reflected through the distance travelled and therefore rate of the drop. So having a greater stride forward will endeavour greater energy transfer and the build-up of more speed and projection, allowing the ball to gain a greater velocity, travelling for longer whilst increasing displacement during flight. Therefore, it is evident that kinematics, momentum, ground reaction force, and projectile motion are all relevant biomechanical concepts that justify the implications of a greater stride forward in an overarm throw, generating a higher launch velocity when compared to a normal stride, as shown in these tests.